In this video, I hope to create free body diagrams of the two masses in the diagram that you can see below and apply Newton's second law in order to derive an expression for the acceleration of this system. So here I have two blocks, M1 and M2, that are connected by a string. And there's another string on the other side of M2, and from that string the two blocks together are pulled up the ramp with a force F. And under the influence of the forces acting on these boxes, they accelerate up the ramp. Between the blocks and the ramp, there is a coefficient of kinetic friction mu k, and the ramp is inclined at an angle theta. And my hope is that I can create a couple of free body diagrams for these two objects in order to derive an expression for the acceleration only in terms of the two masses, the applied force, the angle of the incline, the coefficient of kinetic friction between the blocks and the ramp, and the acceleration due to gravity g. So the first thing I need to do is start adding force vectors to create free body diagrams for these two objects. The first force vectors that I'm going to write are the vectors that represent the weight of either one of these objects, the force exerted on these objects due to gravity. And so object with mass 1 should have a force vector pointing straight down with a weight m1g, and the object with mass m2 should have a force vector pointing straight down with a magnitude m2g. Next, I'll recognize that due to the contact between the blocks and the surface, there's a normal force exerted on each block. And that normal force is perpendicular to the surface and pointing away from the surface always. And so for block 1, that normal force maybe points like this, and I'll call that N1. And for block 2, that normal force might point like this, and I'll call that N2. In addition to those normal forces, there's also a force of kinetic friction that's exerted on each block due to the roughness of the bottom of the blocks and the top of the surface. And those kinetic frictional forces will point opposite the direction of motion, and since those boxes are both being pulled up the ramp, they're sliding up the ramp, those frictional forces will point down the ramp. And so on each block there should be a frictional force pointing down. And I'll label those lowercase f1 and lowercase f2. We're almost done with adding forces to the free body diagram, except we have a couple more to add, and they're related to that string that's existing and connecting the two blocks with mass m1 and m2. The string pulls on each of those blocks, but in a different direction. So let's think about that. The string is pulling to the right up the incline on the block with mass m1, and so that would pull the block with mass m1 up the ramp with a force T maybe. And the string, due to the weight of block 1, would be pulling down the ramp on m2. And for each of the forces that I have in the diagram, I've been calling them N1, N2, M1G, M2G, F1, F2. But for the tension forces, I know that the tension on either side of that string due to the mutual pulling of either block is just going to be T. The tension everywhere in that rope is the same. And so I've just labeled it T, not T1 or T2. And so I think that right now I have all of the forces acting on either one of these objects. It seems that each one of these blocks has 1, 2, 3, 4 or maybe more forces acting on it. And so now what we really should do is try to clean this up a little bit and make sure we understand what direction all of these forces point. But then use our free body diagram to create Newton's second law equations for the x and y direction, and then use those equations to derive this expression for the acceleration that I'm looking for. If I hope to write Newton's second law equations, I really need to define what the positive direction is. And so in order to do that, I'll add a coordinate system to this diagram that I've drawn here. I'm going to say that away from the surface of the ramp is the positive y direction, and up the incline or up the ramp is the positive x direction. And now that I have a coordinate system in place, I should be able to use the forces to write the Newton's second law equations that will help me determine this expression for the acceleration. But before I do that, I think what I'm going to do is I'm going to take all of the forces that I have on these blocks, and I'm going to draw quick sketches, slightly bigger versions of the free body diagrams for each block, so that way I can better show and explain why the forces and equations are matching up the way that they are. And so what I'll do is on the left I'm going to draw a big dot, and this dot represents the center of mass of the block with mass m1. And so what forces are acting on that block? And maybe I'll add a dashed line that represents the inclined plane. Okay. And so what forces are acting on there? Well, we have N1, which pointed away from the surface of the inclined plane. We had M1G that was directed downwards like that. So this is M1G. We had the force of friction, F1, which pointed down the ramp. We called that F1. And we had the force of tension, which points up the ramp like this. Notice the force F, the pulling force F that's applied to the two blocks that pulls it up the ramp, is not applied directly to the object with mass m1. So I think in this free body diagram, those four forces that I have in green, those are the four forces that are acting on the block with mass m1. And so now let's do the same thing for the block with mass m2. I'm going to draw a large dot, and I'm going to draw all of the forces that act on the block with mass m2. And again, I'll draw a dashed line that represents the inclined plane that actually exists behind this block. And so again, we have the weight of the block, which can be represented by m2g, a vector that points straight down. We have the normal force, which points perpendicularly away from the surface, which has a magnitude n2. The tension, which pulls down the ramp, has magnitude t. The frictional force, which points down the ramp, has a magnitude f2. And then, of course, which is not shown in yellow but is shown in red, the force, capital letter F, which ultimately pulls these blocks up the ramp and causes them to accelerate up the ramp. So block 2 has 5 forces acting on it, where block 1 only had 4 forces acting on it. And so now let's use these forces to construct Newton's second law equations for the x and y directions. So I could start with block 1 and say that the net force acting in the x direction is equal to the object's mass times the acceleration in the x direction, where the forces acting on the object and the acceleration of the object are both vectors. And so starting with the forces in the x direction acting on this first object, I know that the tension points up the ramp, and so it's positive, and the frictional force is negative because it points down the ramp. And those are the only two forces that entirely point in the x direction, but a component of m1g also points in the x direction. If you look carefully, m1g has two components, one component that points into the ramp in the negative y direction, and then another component that points down the ramp that points in the negative x direction. And if you know your geometry a little bit, then you know that the angle of the incline, theta, is equal to the angle in this triangle here. And so if you look at the relationship between m1g, which is really the hypotenuse of this right triangle that I've drawn, then you can recognize that the side of the triangle that points in the negative y direction really is m1 g times the cosine of theta, and the component of the triangle that points in the negative x direction really is the sine component of this triangle, which would be m1 g times the sine of theta. And so right now I'm writing an equation for the x direction, so the component that I need to include is that m1g sine theta. And that would be a negative force because it also points down the ramp like F1. So minus m1g sine theta. And those are all of the forces acting in the x direction. And also the object happens to be accelerating, and that acceleration is up the ramp, and so we have a positive acceleration. And so the right side of this equation should be the mass, m1, times the positive acceleration, a. So here we have one of really 4 equations that we're going to write, because for each block we'll write an equation for the x direction and for the y direction. And so here's one of those equations. So now let's write an equation for the net force in the y direction for object 1. In the y direction, I know that there's a force N1 that points away from the inclined plane in the positive y direction. So that's plus N1 minus, there's one more force, the component of the weight, m1g cosine theta, that points opposite the direction of N1, that's in the negative y direction. So minus m1g cosine theta. And those two forces are the only forces acting in the y direction. So that's all I have on the left side of the equation. And on the right-hand side of the equation, I should ask myself, is the object accelerating in the y direction? And the answer here is no, because I've rotated the coordinate system where the positive x direction points up the incline and y is perpendicular to the inclined plane. The acceleration in the y direction is 0. And so here is the second equation that I have for this object. And really what I've got to do now is just go ahead and do the same thing, but for block 2 now. I'm going to write an equation for the x direction and the y direction. So moving on now, I'll write an equation. The net force in the x direction is equal to the mass times the acceleration of block 2. And so now let's shift our focus to the free body diagram on the right-hand side. I know that a force F, capital letter F, points up the ramp and is positive. And I know that there are at least 2 forces pointing down the ramp. I have the tension, so minus T, and then the frictional force, minus F2. But remember, just like we had for block 1, m2g is also a vector that points in neither the x nor the y direction, and so we have to break it down into its components. And the components will work out the same way as before, except instead of m1g cosine theta, I'll have m2g cosine theta, and instead of m1g sine theta, I'll have m2g sine theta. And so in this equation, I'm writing an equation for the x direction, so the component that matters is still the sine component. So minus m2g sine theta, because m2g sine theta points down the incline. This object happens to be accelerating in the x direction, and just like block 1, it's accelerating in the positive x direction. So here I should write m2 times that positive acceleration a. And this is the third equation that we have. And the last equation that we have is for this block in the y direction, which will be a little bit simpler, just like how it was for the block with mass m1. So here I just have 2 forces. The 2 forces I have are n2, which is positive because it points away from the surface of the ramp, and then m2 g cosine theta, which points into the plane or in the negative y direction. And once again, ask yourself the question, is the block accelerating in this direction? And the answer is no, it's only accelerating in the x direction. So the right-hand side of this equation is just 0. And it's at this point that really all of the physics is done. I have analyzed the diagram that I was given and added all of the forces that I could imagine. I've created Newton's second law equations, which include all of those forces, and I was very careful to make sure that if they were pointing in the positive direction that I wrote them as positive, and in the negative direction I wrote them as negative. And I have equations for the x and y direction for both blocks. So really, given any real physical scenario with numbers or you doing an experiment, you should be able to plug in these numbers and solve for any value that is related by any of these equations, whether it be the acceleration or the applied force or the frictional force. But the physics here really is done in writing those equations. But what I'd like to do now is actually answer the question that I posed at the beginning of the video, and that was derive an expression for the acceleration only in terms of those variables. And so what I'm going to do now is I'm going to start combining these equations and actually need to do a lot of algebra in order to figure out this expression, because what you'll notice is that some of the variables in my equations below are not variables that I'm allowed to include in my expression if I'm trying to answer the question that was posed. And so now the focus will shift from mostly worrying about the physics and the forces to really trying to think about how do I do the algebra in order to solve the question that was asked. Alright, so let's actually solve the question. So in the red box, I'm reminding us that I'm looking for an equation for the acceleration, and on the right hand side of the equation I'm only allowed to have m1, m2, the masses, the applied force F, the angle theta, the coefficient of kinetic friction, and the acceleration due to gravity. So the four equations that I found on the previous part of the video I've summarized below. So this is for block 1 and block 2. And now let's use those equations to find the acceleration. I think my plan here is first to try and eliminate t. So notice the tension is not allowed in the equation, so I need to eliminate the tension. And the way that I'm going to do that is, first I'll call this equation number 1. I'm going to take equation number 1 and solve it for t, and then I'm going to substitute that into equation number 2. So notice that here is, right here, there's a tension. And I'm going to solve equation number 1 for the tension here, and then substitute it into equation number 2, and that would effectively eliminate the tension variable, which would be good because it's not allowed. And so the top equation, if I solved the top equation for the tension, that might look something like T equals m1a plus F1 plus m1g sine theta. So all I've done there is I've added the two terms f1 and m1g sine theta to the other side of the equation. And now I have an expression for the tension. So let's plug that into equation number 2 now, which has F minus the tension. And so everything in red is what I'm substituting from equation number 1. m1a plus F1 plus m1g sine theta. But then equation number 2 continues on, right? After that, I have minus F2 minus m2g sine theta equals m2 times a. So I've substituted in the tension, and now let's go ahead and distribute that minus sign. Notice how there's a minus sign in front of the tension force there, so that minus sign needs to be distributed to every term. So really what I have is F minus m1a minus F1 minus m1g sine theta minus F2 minus m2g sine theta equals m2 times a. In the next step, I'd like to do two things. First, what I notice is that there's a term here that has the acceleration in it, and there's a term here that has the acceleration in it. So I'd like to get those two terms, and those only two terms with the acceleration, on the same side of the equation alone. So I will be adding m1a to both sides of the equation. And then the second thing that I'd like to do is write in the expressions that I know for the frictional forces. I know that the frictional force F1 and the frictional force over here, which should be labeled F2, those two frictional forces have equations for them that depend on the coefficient of friction and the normal force. So let's just remember in general that any equation for the frictional force, lowercase letter f, that is given by the equation mu, which is the coefficient of kinetic friction or the coefficient of friction, times the normal force n. And so in this next step, I'm going to not only be adding m1a to the right-hand side, but I'm going to be substituting in an expression which contains mu times n for f1 and f2. So let's start that. I have f minus f1, which is mu k times n1, minus m1g sine theta, minus mu k times n2, minus m2g sine theta. And on the right-hand side of the equation, I will have m1a plus m2a. And so I could write that as m1 plus m2 times a. In the next step, I'd like to also do two things. First, I would like to substitute in expressions for the normal forces. So what I observe is that here I have n1 and here I have n2. And those variables are not allowed in my final equation. And so what I notice is that I have two equations here that include n1 and n2. And if I rearrange those equations to be written like this, if I have it as n1 equals m1g cosine theta and n2 equals m2g cosine theta, then those substitutions would not introduce any variables that aren't allowed in the equation. In fact, they would eliminate those variables and introduce variables that are allowed in the equation. And so in this next step, I'm going to insert m1g cosine theta and m2g cosine theta into the equation, and I'm also going to divide both sides of the equation by m1 plus m2. Notice what that's going to do for me, right? If I divide both sides of the equation by m1 plus m2, I would then have only a on the right-hand side of the equation, which is effectively what I want. And so all of that in the next step looks something like I have f minus mu k times n1, which is now m1g cosine theta, minus m1g sine theta, minus mu k times n2. n2 is m2g cosine theta, minus m2g sine theta, equals a. And that's because on the left-hand side, I should have a fraction where in the denominator of that fraction, I have m1 plus m2. And I'm sorry to say that I really don't think that the equation for the acceleration is going to look any prettier than this, although we can tidy it up just a little bit. If we notice that in this equation there's really a couple different kinds of terms. There are terms that contain mu k, g cosine and theta, those two terms. And then there are terms that contain g sine theta, these two terms. Then we could combine those terms and at least pull out the common variables and simplify this a little bit. And so let's write this final equation. A equals on the numerator f minus, and let's first consider those two terms in green. Those two terms in green have some common stuff. They both have mu k, they both have g, and they both have cosine of theta. So I'm going to pull that out of both terms, and then what was not common to the two terms was m1 and m2, which should be added in parentheses. If I redistribute a minus mu k g cosine theta, I would get two negative terms, the same two negative terms that I have up above in green. Following that, I have the two terms that I put a line over in red, so I should have a minus sign, and in these two terms what was common was the g sine theta, and what was not common was both m1 and m2 again. And again, if I redistribute a minus g sine theta, I would get two negative terms, the same two negative terms that I have up above with the line over in red. And then in the denominator of this equation, I have the sum of the two masses, m1 plus m2. And I think, if you look back to the question that I posed in the beginning, I think we have arrived at an equation that meets the criteria. Here's an equation that in it only has the two masses, the applied force, the angle theta, the coefficient of kinetic friction, and the acceleration due to gravity. And so because this equation meets those criteria, I'm going to go ahead and put a big circle around it. I don't know how often you're going to be asked to use this equation. A couple of blocks on an inclined plane with a string being pulled up the inclined plane. It's not incredibly valuable in the sense that you would use it a lot, but I think that arriving at this equation means that you had to do a lot of work in creating the free body diagrams, and you had to do a lot of algebra in order to get here. And those are skills that are very important in physics. And so hopefully this video allowed you to get some practice working with the equations and working with some free body diagrams. I would encourage you, if you would like to do so as an exercise, to think of reasonable values for f, mu k, the masses, and the angle, and just say things like, well, if the inclined plane was 30 degrees and each of the masses was half a kilogram, what would be the value, the actual numerical value of the acceleration, which this equation should be able to tell you. So maybe as a final step, go ahead and see if this equation spits out a reasonable acceleration for some reasonably selected values of each of the quantities in the equation.